In this video, I'm going to show you how to implement a hash table in C from scratch. I'm going to cover inserting, reading, resizing, deleting, and handling collisions. My name is Karol Moroz, and you are watching Make Programming Fun Again. A hash table is a data structure that maps keys to values. You have most likely already used a hash table in a high-level programming language. In Go and Elixir, they are called maps, in Python dictionaries, in Ruby hashes, and in JavaScript objects. The hashmap implementation presented in this video is inspired by chapter 20 of the book Crafting Interpreters by Robert Nystrom. This book is available free of charge at craftinginterpreters.com. The source code for the implementation is available on my GitHub, and I'll put a link to the repository in the video description. Now, before we dive into the code, let me quickly explain the overarching principles behind hash tables. In its essence, a hash table is just a dynamic array, and in this array, some elements contain keys and values. The elements of this array are called buckets. The reason a hash table can provide fast lookup and insertion times is due to the way entries are stored in the table. Each entry is stored at a specific index, and we can very quickly calculate this index from a key using a hash function. A hash function converts the key to a big number, then we reduce this number modulo the size of the array, and we get the index where the element belongs in the array. This way, we get much faster lookup times than with alternative approaches such as binary search. The hash function we are going to use is called fnv1a. It may happen that two or more keys in the table end up pointing to the same index. This is called a key collision. In this video, we are going to handle collisions using a technique called open addressing. The way this works is very simple. If the index calculated by our hash function is already taken by a different entry, we check the next bucket and the next one until we find one that is empty. Handling collisions is kind of a waste of time, and it slows down insertion and lookup times. You can reduce the risk of collisions by giving your entries enough space to live and grow. The ratio of the number of entries to the table's total capacity is called the table's load factor. We need to make sure it never exceeds a reasonable limit, let's say 75%. If the table becomes too full, we allocate a new array that is 2 times larger than the previous one. Then we copy all elements from the old table to the new one, and finally we can free the old array. Please note that most items will likely end up at new indices in this new array. I am recording this video on an M4 Mac Mini running macOS Sequoia 15.4 using Clang 17. The reason I'm doing this on a Mac is that it's actually a bit more difficult to set up and compile C projects on macOS than it is on Debian, and I wanted to show you the issues you may encounter when linking external libraries. However, I will also make sure that the project compiles on Debian-based operating systems. If you are on Windows, you can set up a complete Linux-based environment using the Windows subsystem for Linux, and then you can just follow all the steps for Linux. In an empty directory, create two files, table.h and table.c, and open table.h in a code editor. Start by adding an include guard. Then include stdin.h so we can use type aliases for integer types. Next, we are going to define our data types, starting with a string type. In C, there is no built-in string type, and traditionally text is stored in arrays of characters ending with a 0, also known as a null terminator. Our string type is going to wrap this array, and it's also going to store its length and the computed hash value for this string. The entry struct is what we are going to store in the hash table. For the sake of simplicity, this implementation only supports string keys and integer values, but with some creativity you can modify it to handle any type of values. Finally, define the table struct representing the actual hash table. This struct has 3 fields. Capacity is the total size of the array, count represents the number of buckets that are currently occupied, and entries is a pointer to the actual array of buckets. Then we declare 3 functions: init table, which will function as a constructor, free table, which is responsible for cleaning up, and grow table, which resizes an existing hash table. Next, open the file table.c. Include the header file we have just written, and we are also going to need stddev.h for null, stdlib.h for malloc and free, and string.h for memset. Now let's implement init table. This function is very simple. The only thing it does is set the fields of a table struct to their 0 values. Free table is even simpler. Free the array of entries and call the constructor again, resetting the table to its default state. Grow table is a bit more involved. First, we allocate a new array for entries. Then we need to initialize all elements in this array to 0 values. We could do this with a for loop, but since all of these are going to end up as zeros anyway, we can use memset to set all the bytes in the array to 0, which will have the same effect. Then we can free the old array and point the struct's entries field to the new array. Then we set the capacity to the size of the new array and set count to 0. Now you may have noticed that this function does not really do what it's supposed to do. We haven't yet written any logic to copy the entries between the two arrays. This is fine because at this point we have no logic to set and read items either, so the table is guaranteed to be empty. Now that we have a bare-bones implementation, we can write some tests. I'm going to use a testing framework called Criterion, which has been recommended to me in the comment section. On macOS, you can install Criterion using Homebrew. On Debian and derivatives, install the package libcriterion-dev using apt. Create a new file called test.c and open it in your editor. Include Criterion's header file and the table.h file we have written. If you are on macOS and have a setup similar to mine, at this point you're going to get LSP errors because clangd will not be able to find the header files for Criterion. You can fix this by creating a file called .clangd in the project directory. In this file, add these 3 lines telling clangd where to find header files for the Criterion framework. Back in test.c, define a test example using Criterion's test macro. This macro takes 2 parameters, the name of a test suite and the name of the test example. Let's call the test suite table and the example init_resize_free because we are going to test the constructor, the grow table function and the destructor. In the test example, declare a table and call init table with a pointer to it. Using the cr_assert_eq macro, assert that all fields in the struct are now set to 0 values. Next, let's write a makefile. On all platforms, we're going to need the linker flag -l_criterion. This tells the linker to link against the Criterion library. Then we're going to add some conditional logic. Using uname, we check if we are building the program on macOS, and if that is the case, we add additional compiler and linker flags to help locate Criterion's header files and libraries. Then we define a target called test, which depends on 2 source files, table.c and test.c. For this target, we use a bunch of magic variables and command line flags. CC stands for the C compiler binary, and this is usually going to be either Clang or GCC. C flags are the resolved compiler flags. -g compiles the binary with debug information. $caret is a special variable that expands to all prerequisites of a target. In this case, it's going to be the 2 C files, table.c and test.c. $o$at is going to expand to -o test, meaning that the linked binary will be called test. Finally, LD flags are the resolved linker flags. After this command, we execute the compile test binary. We mark the test target as a phony target, which means make will always build it and execute it, even if the underlying C files haven't changed. If you run the tests now in a separate terminal, you should get a pretty and colorful message telling you that the tests have passed. Now that we have the initialization out of the way, we can start implementing the actual storage logic. And to this end, we are going to add 3 more functions to this header file. I'm going to declare the function called copy string, which is going to create a string instance based on a char array, and another one called free string, which is going to do the opposite. And this function is also going to be responsible for hashing strings, or more specifically, it's going to call a hashing function. The reason we are storing the hash on the string is because this way we only have to hash the string once. Another function we're going to implement is going to be called table set, and we are also going to implement a table get. And this is going to accept a pointer. So the way these functions are going to work is that table set is going to take a pointer to a table. It's going to take a key string, and it's going to take a value which we are going to insert, and it's going to return true if the key was a new key, and false if the key has already existed in the table. In both cases, the item is going to be inserted, and then the table get function is going to return false if the item does not exist in the table, and true if the item got successfully fetched from the table. And the actual value is going to be placed in the pointer, which we're going to pass as the third positional argument. So now in table.c, we can implement the actual hash function, and the signature is going to be static. It's static because we do not need this function anywhere else. It's going to return a 32-bit integer, and this is going to require including stdin.h. And we are also going to be using uint_t. And the function is going to be called hash string, and it's going to take a pointer to a string, and it can even be const because we are not going to modify that string. And the function we are going to use is called fnv1a. And the way it works, we start with a specific function. In the variant we're going to use, this is this number, and we need to use the u suffix, because otherwise this literal might be treated as an signed integer and it might be truncated. It may have different sign. I haven't seen this in action, but this is the way the book actually used it. And then we're going to iterate over every character in that string. So actually we could just iterate it like this. Yes, so my idea is that we can just dereference the pointer for every character, and then we can say hash equals hash, and we XOR it with the character as a uint_t. We can just say chars at 1, and then we multiply it by this number, and this is a prime number, and it's like a divisor of this big offset thing that we used. And then we say chars plus, and it still seems to work. Okay. And then we return the hash. So basically we are not going to use a for loop. We are only going to iterate the pointer, and then in string pointer copy string, in this function we are going to accept a pointer to the characters, and we are going to return a copied string. So we can say uint32t hash equals, or even like this, string pointer string equals malloc size of string, we need to actually allocate a pointer, because we cannot return a function, an instance created in here, because that would be a stack variable and it wouldn't live past the lifetime of this function. So we need to allocate it on the heap instead. And then we can say that strings hash equals hash string chars. String length is going to equal strlen, and this is also going to take chars, and then string chars equals string dup chars, and we return this actual string pointer. And I think strdup and strlen come from string h, so we can also add them here as strdup strlen, like so. And then void free string is going to take a pointer to a string, and we're going to free the string's chars pointer, and then we're going to free the string pointer itself. Okay. The next function we have declared but not defined yet is going to be table set. Bool table set, like so. So the thing we're going to have to do is we're going to find an index for this new item, but first we need to check if the table's count +1 is not greater than max load factor times table capacity. And this max load factor we have to, I call it table max load, okay, sorry, like so. So if this is the case, we're going to have to grow the table to the new capacity, and the new capacity is going to be, if it's less than 8, we're going to return 8, and otherwise we're going to return double the capacity. But realistically, with modern computers, RAM is pretty cheap, and it's sometimes easier to allocate a bigger table and then just grow it less frequently. So I think Elixir actually uses like 32 element long maps by default. And so we grow the table, and then we're going to have to find the index. So we're going to implement a new function called findEntry, and it's going to return an entry. And it's going to take the pointer to entries, it's going to take the capacity, and then it's going to take the key we want to find. And I'm going to also define it as a static function. So static entry pointer find entry, taking a pointer to entries, const int capacity, and string pointer key. And now what's going to happen is if a capacity is 0, we can be sure that there is not going to be any entry at all, so we can just return null. We start with an initial index, so it's going to be int index equals key hash, and we could do a modulo by capacity, but actually what we can do is, since capacity is always going to be a power of 2, we can just use a binary end, and this way it's going to basically return the same result, but it's a few cycles faster. So then we're going to do an infinite loop, and we check the entry at the index. So if entries at this index, if the entry is null, or we compare the key, entry key, return entry, otherwise entry index equals index +1 and capacity -1, like this. So compare keys doesn't exist yet, so we're going to have to define it. And it's a boolean, it returns a boolean, so we also need to add stdbool, the stdbool header, because this is what defines the boolean type in C. And it's going to so static bool compare key, and it's going to be string pointer A and string pointer B, like this. And what we can do to compare is we can first compare if the lengths are the same, because if the lengths of the string are not the same, it's definitely not the same string. Then we can compare the hash, and then we can actually do a string comparison for just in case there's any other collision. So strcmp A chars and B chars. We could even probably do strncmp or something, and then we can make it ALEN, like so, and we compare that it equals 0. So if you are new to strcmp, it's the way strings are compared in C, and confusingly it returns 0 if the strings are the same. And I use strncmp, so it's limited in memory to the length of those strings. So what this find entry function does is we look for the bucket where we can put our entry or where we can find our existing entry. And the way this works is, firstly, if the array is empty, we are definitely not going to find our entry, so we can just return null. And then, as mentioned earlier, we take the hash of a key and reduce it modulo the capacity of the array, and we get the index where we should start looking. Now the thing is, as I mentioned, reducing something modulo a power of 2 always equals to doing a binary AND. So this is like this tiny optimization I did here. And here we have an infinite loop. It doesn't really have a condition to return other than finding an empty slot or the correct key. But since we know that the table will always have at least 25% of the table are going to be empty, or that we can find the key, this means we can be sure it's not going to result in an infinite loop. And if this is the way we are handling collisions, if we did not find an empty bucket, or if we did not find the key that actually matches the one we are looking for, we try the next bucket, and we are just looking at the next one, but we are reducing it modulo the size of the array. And this way, if we go past the end of the array, we start from 0. And this way it's going to wrap around. Okay, so once we found the entry, we can now say entry key equals the key, entry value equals value, and entry and table count ++, like so. And oh, and by the way, wait, no, this is never good. If entry's key equals null, if the key is null, so I made a mistake in find entry. We are not supposed to be looking for an entry at this index. We're not checking the whole entry. We're not checking if the whole entry at this index is null. We're checking if that key is null, because this means that entry hasn't been set yet. And here we can say const bool is new entry equals entry key equals null, and we return is new entry. Okay, so we could try and write a test to see if this at least does not crash. So I'm going to define a new test example. I'm going to call it table set, and table t init table t, and then I'm going to const string key equals copy string foo, and we can try and set this key on the table, and the value is going to be 42, and then we can assert EQ that the table's count equals 1, and assert EQ that t capacity equals 8, because we have expanded the array, and then we check that the entries is not going to be null. Like so. So now let's see if it passes. Okay, it seems to have passed, and now we can okay, let's see if we can find this entry at an actual index, like so. I'm going to set it to -1, and then for int I equals 0, I is less than t capacity I++. We check the entry at this index, so it's t entries at I, and then if entries key is null, we continue, and then if entries key entries value, we can just check if the entries value equals 42. We know that this is going to be this value, so the actual is going to be set to I, and we can break. Or we don't even need this one. And then we can assert EQ that the okay. So now we can get the entry at the actual index. So entry equals t entries at actual. You know what? We could actually just make it like this: entry actual equals null, and then entry equals this one, then actual equals entry, like so. So we search for this specific entry, and then we can assert that the entries, the actual entries value is 42, and we assert that the actual key equals our key. So because it's definitely going to be our key, because we are basically just assigning a pointer. Okay, we can do some debugging like this. The actual actual index equals -1, actual index equals -1, so actual index no, actual index is supposed to be I. Okay, so we know that foo ended up at index 7. And the reason I used printf and not an actual debugger is that with Criterion it's actually pretty difficult to debug, and I still haven't figured the proper way to debug it. So unlike CUnit, where you can just debug the binary, with Criterion you actually have to like start a debugger server and then connect to it, and I haven't figured it out yet. But hopefully I can figure it out later. And in the meantime, we can modify the grow table function. So this is basically just a placeholder implementation right now. We said that we want this function to copy elements from the old array to the new one. So let's say if tables count is greater than 0, we copy everything in the array. So for int I equals 0, I is less than table capacity I++, and then so we take the entry at the index, so table entries at index, and we take a pointer to it, and then we are going to actually we're going to have to we may have to reassign. Wait, how was it done in the old? Wait, I'm going to check my other implementation. Okay, so the way I did it in the in another attempt is we basically have to we're going to have to find the destination bucket. So it's going to be find entry, and this means that this find entry implementation will have to go much higher, like in here, and we find a new entry. So it's going to be, and we're passing the new entries, we're passing the new capacity, and we're passing the entries key. And also if the entries key is null, then we can continue, because it means that there is no entry in here. So we set the destination's key to key, and we set the destination's value to the and the destination's value to this entry's value, and then we iterate count. Yeah, and then this could be set to count like this. Okay, I think this will work. This is not exactly the implementation that was in the book, but it's fine. And I think we could write some tests to check actually getting items from this array. So I'm going to rename this function table set get, and I'm going to rename this test table set get, and I'm going to do this with using I'm going to check that we can correctly set the value, set and get the value using table get. So int actual equals -1, and then bool exists equals table get. We pass the table, we pass the string, and we pass a pointer to actual, and then cr assert. Does this exist? Yes, it does. Assert exists. You know what? We could actually just pass all of this into this macro, and then cr assert eq actual 42. And when we run this test, we're going to get a linker error because we haven't implemented table get yet, which is basically a perfect example of test-driven development. So why doesn't it get filled up? Table, string key, and int pointer value. So we search for the entry, and we pass the entries, we pass the table's capacity, and we pass the key. If entries key equals null, we return false. Otherwise, we set the value pointer to the entry's value and return true, like so. And let's see if this compiles. Okay, it does compile, and we can get the proper value using this function. And the most difficult part of the actual hash table implementation is going to be deleting entries. Even though it sounds pretty easy, it's actually more convoluted than you may expect, because we are going to have to we cannot just delete a value. We have to set it to a value called tombstone, and this tombstone thing is going to be just a special value we're going to use. So we're going to set the tombstone can be anything. It'll be any value as long as you can unmistakably check that it's actually a tombstone and not an actual value. And basically for our purposes, it could be something like tombstone value could be -1, like so. And we can define table delete. We can even do it at bool table delete, like so. Table, pass the pointer to a table and pass a string key. And then what we're going to do is we search for an entry. So entry equals find entry table entries, and then table capacity and key. It's basically going to be very similar to this one. If the entry's key is null, we return false. Otherwise, we set the entry's key to null, and we set the entry's value to tombstone value and return true. And this is going to mean that this value used to exist, but we basically have to make sure when we search for entries, we basically have to make sure it did not exist before. And what we're going to do is in here, we're going to take it into account when searching for an index. So if the entry is key in here, if the entry is a tombstone, go ahead until you find a new a truly empty value or the desired key. So you can basically say something like static bool is tombstone entry return entries key is null and entries value equals tombstone value. So we are going to store the pointer to the first tombstone we encounter, and if we wait, was this the way it worked? Let me check the actual implementation in crafting interpreters, you know. So okay, yes, so this is more or less the way it worked. So the way this works in the book is we check the entry at the index. If the key is null and there is no value, it means it's an actual empty entry. And if we were looking for, and now basically if the value, so this means we did not find the actual key, so we can repurpose the tombstone. So what this means is, okay, if entries key equals null and if entries value equals 0, return tombstone is null, then entry, otherwise we return the tombstone. And this is an actual empty entry, actual and empty bucket. Return first tombstone if ever one was ever found, and then if the entry value is not 0, this means we have encountered a tombstone. So if tombstone is null, we store the current entry as a tombstone and we continue. And yeah, I think we continue. Like so. Was it? No, we do not continue. If we compare if the key. Okay, this is actually going to be an else if, I think. And this way we can repurpose tombstones. And when we set things in the array, is new key, okay, like this is new key. Okay, yeah, so this means that if we're also going to only increment the count if the entry was an actual empty entry and not a tombstone, because we should count tombstones towards the load factor, but we should not increment them if we repurpose an existing tombstone. So if the entry value, if is new entry and entry's value is not tombstone value, then we increment the count like this. And let's see if this still passes. Okay. So now let's see if we can test deleting table delete. Delete entry. I'm going to call it delete entry. So just like before, we declare a table, we initialize it, and then we're going to set some keys. Actually, we should probably make like a bigger example. So I'm going to define a type in here, and it's going to be actually it's going to, we can just repurpose the entry now. So static const entries equals oh no, I cannot do it. Wait. Type def test struct. I cannot do this because the actual entry type we are using in the hash table uses the string type, and in the test I wanted to use character arrays. So I'm going to just call it test entry, or even like lowercase test entry, and it's going to take a keep, which is a char array, and it's going to take an integer which is going to be a value, and yes, test entry like this. So we're going to insert full with the value 42, and we're going to insert bar with the value 69, and we're going to insert buzz with the value of 420, and then for int I equals 0 n equals size of entries divided by size of test entry. I is less than n I plus plus, and what I did here is I calculated the size of entries by dividing the size of a total variable by the size of an element, and this way you get the element count. So I'm going to copy the string, and test entry entry equals entries at I. I guess I can make it const. So we copy string, which is we copy the key from the entry string. We copy the string from the entry, and then we run table set table key and the entry's value, and then we can assert that the table's count equals 3. Okay, and then table delete. Okay, string key equals copy string foo, and we delete the foo element. So wait, I'm going to make sure that we can still fetch the can still fetch it here.
like so, and assert that this returns true. And then let's see. Is there like an assert? Is there like a refute macro? No. Is there like a cr assert? Not. Okay, I guess. cr assert not table get t key. Okay, I'm going to reset actual to -1, and I'm going to assert that we cannot fetch the actual value from the array anymore, and I'm going to assert that the actual value is -1. Okay, this is looking good, and I think we should probably write a longer test to test how the table will behave if we actually had to grow it. So I'm just going to give it like 8 entries. So yeah, BPs is going to be 1, and then booty is going to be 69, and then BP in all capital is going to be 2, and at this point we are at 6 entries. So now I'm going to make a all capital foobar, and it's going to be 3, and we are at 7, and with like mixed capitals BPs is going to be 4, and let's test if the table is growing correctly. So let's grow and get. So I'm going to test if the table grows beyond these boundaries, does it still correctly copy all these elements. So I set all these entries, and I'm going to assert that the count is going to be 8. Wait, what? Why is it not 8? What's the actual count? Printf. Okay, so I think we found the first bug. What's the count? The count is 3, and why? It's because we are testing with the wrong array. Okay. Okay, will it work now? Okay, it works. And let's assert that the capacity equals 16. Okay, and let's assert that we can actually fetch an element from the array. And let's take a different one this time, like we take baz, and let's assert it equals 420. And it works. Also, there is something I did not mention in the heavily edited version of the first part of this video, and it's that this entry thing, you can actually make it an int 64t. And the reason being is that this struct is going to be 16 bytes long no matter what, because the string pointer is going to be 8 bytes long on 64-bit architectures. And if we only use a 32-bit integer, we are kind of wasting space, because the compiler is going to pad it to be 16 bytes long anyway. So might as well use a 64-bit integer in here. And this kind of concludes this tutorial. You may have noticed that the formula was a bit strange because the first part, like until this point in the code, was recorded and heavily edited, but this was going very slowly, so I decided to just freestyle the rest. And hope you don't mind. I hope you don't mind it. If you have enjoyed this video, please like, and you have really enjoyed it, maybe you consider subscribing to my channel. And there is a waiting list to join my channel's Discord. The last time I checked, there were 4 people on the list. The address is discord.moros.dev. There are 4 people on the list, and you can join it in here. The source code of this application is available on my GitHub. There is a link in here and in here, so you can see that there is nothing nefarious going on. And yeah, I would be very glad to actually collect 100 faithful subscribers who are willing to join my Discord. And before that happens, thank you for watching, and I will see you in the next video.